In Chapter 7, Part 3, we're going to look at the periodic trends for ionization energy and electron affinity. So ionization energy is the amount of energy it costs to create a negative ion, or how much does it cost to remove one electron at a time. So we tend to think about I1, I2, or successive ionizations. So what does that mean? So I1 is the first ionization energy. So this is to remove the first electron. So what we see in this case would be for sodium, it would be sodium gas goes to sodium plus E minus. So the ionization energy is to remove the first electron. So up here it says that it should create a negative ion, and so it's actually the ability to create a positive ion plus an electron, which is in fact negative. So we're going to remove one electron at a time, which means that I2, the second ionization, would be to actually take the Na plus to Na2 plus 1 E minus. So you'll notice that every time you remove one electron at a time. So it turns out that the ionization energies I1 is less than I2, is less than I3, is less than I4, and so on and so on. In increases due to the increasing Z effective. So for every electron you remove, the Z effective is going to become stronger, and so the electron cloud will contract over time. So let's think about this in terms of a trend both within an element and without. So on your slides, you should see a table. And so I'm going to recreate parts of that table, but definitely not all of it. So let's think about aluminum. So I1 is equal to 578. I2 is 1817. I3 is 2,745, and these are in kilojoules per mole. And I4 is 11,577 kilojoules. So if we look at these, we have roughly the same gap here and here. These are similar values. So what leads to this massive explosion between I3 and I4? So let's think about this in terms of, let's see if we can set that up, the electron configuration. So for aluminum, it's going to be 1s2, 2s2, 2p6, 3s2, 3p1. And so when we look at Al plus, we're going to lose that last electron, so 1s2, 2s2, 2p6, 3s2. Okay, that kind of makes sense. That electron's alone. It's probably easy to remove. So Al2 plus would be 1s2, 2s2, 2p6, 3s1. All right, kind of makes sense. We're removing electrons out of the n equals 3 shell. So Al3 plus is 1s2, 2s2, 2p6. So we remove the last electron out of the 3s electron. So now we've reached the noble gas core. And when we go to make Al4 plus, now we're removing an electron from a fully filled shell. So this 2s, or the 2n equals 2 shell, is very full. So this large distance here, or the large difference, tells us when we break the noble gas core. So if you look at the table in the graphic on your slides, you'll see that this is true as you start to look at different electrons or different elements. You can see, okay, as we go across, there will be a big gap. That big gap will tell you whether you're moving from the n equals 2 to the 1 shell or n equals 3 back to n equals 2. So the trends for ionization energy. So generally increases across the row. So we'll draw up our little periodic table. And so we see increase. And it generally decreases. So when we look at this, you can see that there are probably some places based on the subshells. If you think about a p orbital, you might see something slightly differently. On this slide in your handout, you will see a graphic that gives you finite values. So the S and the P block elements show a larger variation in I1 than transition elements. By and large, we will compare S and P block elements, which don't forget are these elements and these elements, when we compare trends for I1. The trends for ionization energy 2 are quite different because it matters if you're removing an element from a shell or not. So the ionization energy trend typically looks at what do they look like for I1, or I can give you a table like we saw on the previous slide and say, can you identify an element? Or we can look at some of the other values in this case, or we can write the equation. For example, the fifth ionization of, we'll talk about phosphorus. So that would be the phosphorus 4 plus goes to the phosphorus 5 plus 1e minus. And so this right here tells you what the charge is of the element at the end. So let's look at these values and rank them in terms of increasing I1. So our full shells are going to be neon and argon. And so neon is slightly above, and so the trend says it decreases as you go down. And that will be the same for potassium and sodium in the opposite order. And because it is leftover, phosphorus will go in the center. If you are not sure, write out the electron configuration, and that will tell you about the ionization energies. So the last periodic trend we want to talk about is electron affinity. And so this is the energy required to attach an electron or the change in energy when an atom becomes an anion by adding an electron. So the electron affinity in this case, if we were thinking about chlorine, so chlorine plus 1e minus gives you chlorine minus. Chlorine minus plus e minus would give you chlorine 2 minus. So they are successive just as they were with ionization energy. And so what we'll see is that it creates the anions. So it is somewhat similar and almost the inverse of the ionization energy. Now for some elements such as argon, so argon plus E minus to create argon minus, the delta E in this case is greater than 0. This means this is very unfavorable. So when the electron affinity is greater than 0, this tells you that when the element takes an electron, it basically gives it right back. And so in this case, these will not accept an electron. So there are some quite negative values, such as chlorine. And so in that case, we can see this. So if it's greater than 0, the elements are unstable. So if we look at our periodic table, what we will see is no change as you go down. And it increases as you go across. Now you'll notice that right here in the center for things like nitrogen, the delta E, or the change in energy, is going to be greater than 0. So nitrogen has a half-filled shell. And would prefer not to take an extra electron in order to violate Hund's rule. So has a half-filled shell, so does not accept an electron. So for half-filled shells that are quite stable, we will see a delta E greater than 0. So it's always tricky to kind of look at that in this case.